What's up? Bogdan Lazars here, and this is my first tutorial ever, so don't judge me too harshly. I'll try to do my best to keep this consistent and interesting for you guys. Also, I'll try to speak my best version of English to date. My main goal for today is to build a sun, or a star similar to our sun, completely in Houdini from start to end. My background is artistic, so don't expect too much technical wizardry around here. This tutorial will show a way, a noob way, let's say, to resolve problems in Houdini, to collect information from the net, put everything together and finish a project. Okay, so I did my research and I bumped into these videos released by NASA a couple of years ago that I liked, and I think that they are the most realistic representation of the sun that you can find free on the net. So watching this, I decided to split my project into two parts, into building the sun body first, and then trying to build the solar activity or the explosions. For the sun body, I think the way to go is to use curl noise, and for the sun explosions, I think I will use particles, and I will move these particles using a vector field in the shape of the magnetic field. So I needed to know more about magnetic fields, so I searched further and I discovered this page, also from NASA, that is dedicated to solar magnetic fields, and they have a lot of simulations and a lot of research that is public. So what I've learned is that the sun is covered with two types of magnetic fields, big ones and small ones. The big ones stretches further away, and they're called open magnetic fields because the fields never come back. They leave the surface of the sun and stretches out for millions of miles. And the small ones, who leaves the surface of the sun just for a short period to come back after that, back to its surface. The small magnetic fields are generated by those black and white spots in these simulations. In this simulation, those spots are so-called sunspots. They are highly charged magnetic fields with thousands and hundreds of thousands of Gauss, and they run freely and chaotically over the surface of the sun, generating this mayhem of magnetic forces. So I will try to build this into Houdini. So let's see how to do that. So I decided to start with the magnetic field because I think that this is the most difficult one, at least for me. And reading about it on Wikipedia makes my head explode. And I realized that my knowledge of physics is not enough to do it by myself. So I tried to find some other examples from the net, from other people, and I bumped into two. The guys from Entagma had a tutorial, a short one, but it's mainly focused on the Newtonian laws of attraction rather than magnetic fields and visualizing the magnetic fields. And the other one, which I like and at least suits my needs better, is from Alexandru Pepe, and it's a very nice piece of work, simple and efficient. And I will try to adapt this one to my needs. So let's start. Okay, so I will start simple by building only two poles, a negative and a positive one, and simulate a magnetic field between them. And if this works, I will apply the same algorithm over the surface of the sun. So let's start by building a point. Another transform node, just to position it in space. So this one will be the positive pole, for example, and I'll do that by using vex. I will make an attribute called pole, a float attribute, and I will assign a value of 1 to it. So now I have the positive pole and I need the negative one, so I'll duplicate this and move it further away, and I'll change its value from positive 1 to negative 1. So now I have two poles, one with plus, the other one with minus, and I need to build a vector field. To do that, I will use VDB volume because it's faster than other volumes in Houdini, mainly because it's a sparse volume and have a low memory footprint, and also has fast access to its voxels. So let's build a VDB. Give it a name, magnetic field. Type will be vector float. The voxel size, we will leave it like that for now. Because VDB, it's a sparse volume, that means exists only where we want to. So we got to define the area of existence for this VDB, and I will do that with the bound. And I'll say that it's 0.4, for example. And I'll copy those parameters and references to the upper padding. Okay, it's pretty big. I think we can go smaller. Now VDB should be activated all the time, constantly. So let's activate the VDB using this bounding box. So I will reference here the bounding box. And now we have a volume. Now I need a way to visualize the insides of the VDB. Actually, I want to visualize the future vector that will live inside this VDB. And luckily Houdini offers us a node for that, and it's called volume trail. And what this node does, it samples the vector fields in the points specified by the first input, and draw curves following the vector volumes connected to the second input. So we need some points to work with, and to obtain that we will populate the inside of this bounding box with a fog volume. Okay, this fog volume right now it's not so dense, so we'll raise the sampling divisions, and we will scatter points onto it and into it. So we have 1000, let's go for 2000, and connect the VDB to the volume node inputs and the points to the points inputs. We will see some curves that right now don't represent anything because we don't have a vector yet. So let's build one, and we will use vex again, but this time we will use the volume vector to write it down. Volume wrangle, sorry. Okay. Let's set the values. Let's put it 1 on the x-axis, 0 on the y-axis, and 0 on the z-axis, and see what we have. Now we have some horizontal lines that resembles the horizontal vector that we just created in vex in the volume wrangle node. So we have a good environment to visualize our future magnetic field. So let's build it. Before we continue, let's take a step back to theory and think how to build our magnetic vector field inside our volume. So what I did draw here is the setup that I have right now in Houdini. The VDB volume and the two particles, the negative one and the positive one. And what I really need is to calculate the direction and the magnitude of vectors inside each of those voxels that later on will become the driving force behind our particle movement. So let's take a position in our volume and call it vector P. and try to calculate the direction of the vector and the magnitude for this specific voxel. So what we know is that this voxel will feel the negative charge of P1 and it will be repelled by it, and it will feel the positive charge of the vector of the point P2, and it will be attracted by it. Let's give those vectors some names, V1 and V2. And now to calculate our magnetic field, we simply add V1 and V2 together. Vector magnetic field equals V1 plus V2. So it's easier to say than done, but the problem is how to calculate the V1 and the V2, how to find out the direction and the magnitude of those two vectors. And here the credit goes again to Alexander Pepe, because he was the one who solved the problem. But before I dive into it, let me arrange the things a little bit around here, make more space. Okay. So if we calculate the vector distance between our voxel and each of those pole positions, we will obtain a vector which is pretty small when it's close to the pole, and it will grow very big when it's further away. So that's not what we want. A magnetic field is exactly the opposite. The closer we are to the pole, the stronger it gets, and the further away we are, the weaker it gets. That's why in our calculation we should use the inverse of the distance from each pole as a multiplier for the distance vector, for the normalized distance vector. So it goes like this. Vector V1 equals our pole multiply by the normalized distance, vector distance, which is our position of the voxel minus P1. Vector 2 is the same. Minus P2. And now, as I said, it's time to multiply each of those vectors with the inverse of the distance. So by doing this multiplication, we are sure that our vector is stronger when it's closer to the pole, and it's get weaker when it's further away. So once we clear that, it's time to go back to Houdini and implement this into Vex. So I'm back on the mothership, and let's start write this down. For coding I will use Sublime, which is an external editor. And I choose this one because it has a Vex package, syntax package, so it goes very well with Houdini. What I prepare here is a pseudocode, a description for whatever we'll do here. It's a good practice to do that, especially when you are a beginner like me, because it helps you to organize your thoughts and plan your work. So we will start by opening a point cloud to collect all the information from our points, our pole points. And we will store that into an integer called handle. PCOpen is the Vex function. We should tell the input that we will receive our information from. In our case is input 2. Then the string P, then the vector P. Now we should define an area of search in Houdini units, so let's say 100. It's a float. Then the number of the points that we want to iterate over, So let's put 100, even if we have only 2 right now. Now let's initialize our magnetic vector field. Let's put all the values to 0. Now let's do our while loop to iterate through all our points. Sorry for this OCD behavior, but time to time I have the urge to arrange things into my working space. Okay, so what we did for now was only to open a point cloud to access information from our points. To understand more about it, about point cloud function in Vex, check this little tutorial from Vishang Sach. Here is the webpage, and it's explained in detail and it's very useful. Now that we've done that, it's time to calculate our magnetic field. First thing first, let's define our variables. So the float, pole, and the vector points. Then we will use PC import function to import data from the point cloud file into our defined values. So for the pole, we will write it like that. From the handle, the pole value to our variable pole. Same thing for the position. We will grab the position, the P, and assign it to our PTS. Okay, so I hope you guys didn't fall asleep because I was about to do so, because now it's time for our first calculation. After all this work, we should finally start to calculate the vectors. The first one will be the distance. So vector dist equals vector P minus PTS. So that was it. Now, every respectable vector has a magnitude. So let's give one to our fellow down here by creating a float called magnitude, which equals, and here we will let Houdini calculate that for us with his function called length of vector dist. Let's normalize now the distance vector. We'll build new vectors normalized called ndist, which equals normalize vector dist. Okay, so the grand finale is here. It's time to calculate the magnetic vector. So let's refresh our memory with the equation. So we have our poles, we normalize our distance, and we got to multiply everything with the inverse of the distance. And the only modification that I will add is that I will multiply it with the inverse of the square distance, because I discovered that it's more realistic. So let's do that. So mag vec field equals pole multiplied by normalized distance multiplied by the inverse of the square distance. Okay, and last but not least, let's assign this to our voxel field, voxel magnetic field, which is V magnetic field equals, let's see if there are some errors. Oh yes, here we should add plus equal, because we should add the magnetic field to the equation all the time. Okay, so let's try to put this into Houdini to see how it works. We got to connect the points into the second input, because we said here that we will open the point cloud from the second input. So connect to the second input, and voila. But I guess we have a mathematical problem here, because the magnetic field is running away. Okay, so back again. I identify my mistakes, and I did a lot, unfortunately. So let's correct them. First one, and most important, is the fact that I forgot to make a correct square for this vector, for this float, by putting two brackets. So let's copy again the code, put it back here. Okay, still not good, because I put the wrong input to our points. Should be the points, sorry, not the bounding box. Okay, and now it's better, but still got to fine-tune some stuff. First, the VDB should be displacement, velocity, acceleration. The activate should be 0. Let's change the visualization here, because I don't like this infrared. I prefer the black body. And what we can see is that the fields are pretty powerful. So either we split apart those particles or tune down the power of the poles. I will just split them apart a little. Let's change this background to something more seeable. And now we have a magnetic field. Let's increase the bound here. Oh, too much. And voila, they interact nicely. Maybe I could lower down the scatter to have a faster visualization. So done, we have a magnetic field. Hello and welcome back. So let's review what we have for now. We managed to simulate a magnetic field inside of a VDB volume using VEX. We can visualize it with the use of the volume trail node. And we build a flexible algorithm that allow us to feed him with as many magnets as we want. We can see the positive charge, the negative charge and the positive charge, how the negative repels the vectors and the positive one attracts them. As a fun exercise, we can multiply it to show the flexibility of the system. Multiply the magnets. So right now I have another negative one. I will move this into a different place and feed him, just feed him here. and voila, it's integrated perfectly into the system. You can see here the border between those two positive poles, how they repel each other. So we have everything we need to go further. The next step is to build the surface of the sun, the magnets from the surface of the sun, hundreds of them, animate them to move chaotically over the surface of the sphere, of the body of the sun, and then feed them into this system to generate the actual magnetic field of the sun. So let's do that. First, let's build the sun body, which will be simply a sphere. Let's make this bigger, 5. Let's make it a polygon mesh and increase its resolution. Let's go back to black background. I prefer this one. Okay, let's hide the magnetic field to see only the node that we are working in. Let's put it a name. It's a good practice to name everything. I didn't do that for now, but I will do it from now on. So, sun body. Okay, so what I want to do is to scatter some points over the surface of this sphere, then simulate them using pop, and make them run away over this surface chaotically and stick to the surface. So first let's add normals. Okay, then scatter. Okay, I'll make those 800 should be enough. Change the seed. They are too ordered right now, so I'll try to change the distribution. Okay, so that's good. Now let's emit particles from those points. Build a pop network. Houdini already do a network arrangement for us. So for source we should use all points. Then at birth we should tell the system to give us points only in the first frame and then stop generating more points, because I don't want to have hundreds and thousands of points added frame by frame to the system. So we will do that by using the expression simulation frame is smaller than 2. So whenever it's smaller than 2, be active. When it's bigger than 2, stop it. So if we hit play now, nothing happens, and that's because we don't have any force that applies to we don't have velocity that will move our particles, and we don't have any other forces to move our particles, so we should build 1. As you remember from the beginning, I just said that the body of the sun resembles or looks similar with the curl noise from Houdini, the curl noise of Houdini. So let's do a curl noise and tell this curl noise to move our particles. I'll do that in using pop-vop. Okay, so we need a curl noise. We will add this curl noise to our current position of the points, and then we will add this result, we will add it to our velocity and feed everything into the position, into the velocity. Let's promote those parameters. to access them outside the VOP node. Let's go out and see what we've done. And nothing, but why? Everything should be okay. Oh, there is no input. Okay, so my VOP node wasn't connected to the network. So now we add velocity in a form of curl noise to our points, but as we can see here, the velocity is pretty big, and my magnetic poles are flying crazy all around the space. So let's tune this down a little bit. Let's put here a small value, roughness the same, attenuation also small. It's better. They are still not stick to the surface, they fly around. So let's do a system that tells our particles to stick to the surface of the sphere. And to do that, we will use, you guess it, volumes again. So before you hate me, just give me a chance to explain you why. So, another awesome drawing for you guys. So this is my sun, and those are my crazy particles running all over the place. What makes them move is the velocity. So each of my particles have a velocity that push them into their own business. What I want is to take them from their location and displace them to the surface of the sun. It's like projecting them to the surface of the sun. To do that, I need to find the distance between where the particle is and where the particle I want it to be. Now, what is velocity? Velocity is a vector. So what better house for vectors do we know in Houdini other than the volumes? So let's give them a house and put them inside to a volume. Now, volumes inside their voxels can store informations and variables that will tell the vectors what to do and where to go, like distance in our case, or direction. Luckily, this VDB volume, if you will use VDB, have something called sign distance field. And what this does, it stores distance information between each voxel, each cell, and the ISO surface. And that will give us the distance between the particle and the sun. For example, this particle over here, which resides inside this voxel, will know its distance to the surface of the sun because the voxel know the distance to the surface of the sun with the help of the sign distance field. Now that we are able to find out the distance, we only need the direction. We will move this point with a certain distance to reach the sun, but we don't know in which direction. So the Wonder VDB offer us also direction in the form of gradient. So what gradient is? Gradient is a vector field with vectors that are pointing to the biggest increase of the function. That means that it points outwards from the surface in our case. And it's everywhere inside this VDB. Every voxel, every cell has its gradient. The only problem is that it points outward, that the direction is going away from our surface, and we need to conform our particles towards the surface. So we will simply use the inverse of the gradient and we'll push them with the distance from the sign distance field. We will push them towards the sun sphere. So let's do that. Okay, back into Houdini. Let's build the VDB. We will use our sphere. We will choose VDB from polygons. We will make our voxel smaller to have a higher resolution. And we'll extend the exterior band voxels to, let's say, 50, to be sure that we'll catch all the particles that we will leave the surface of the sun. We'll try to leave the surface of the sun, so we will catch them into this space and push them back with the use of gradient and with the use of sign distance field. Now let's plug this into the second input of our particle system. Then go inside the particle system, rename this node to curl noise, and make another VOP to build our VDB. Let's bring in the volume, gradient, and the volume sample, and we should connect the volume from an input, so we should specify an input. So let's go back here and choose input 2, which is second context geometry. What this does, reference the second input from our popnet. I could put it also here. Let's connect that to our nodes. Let's take the position and sample the position of the points. Now the gradient, as you remember, should be reversed, so let's negate it. Let's multiply. Let's bring those together. And now take the position of our points and add the new position driven by the gradient to the current position, and just plug in to position. And that's it. Now we should see the magic of VDB. Voila. The points now moves over the surface of the sun. Okay, so what we need now is a way to make those particles move a little bit more liquid-like. First of all, I don't want them to cross one through each other. I want them to bump into each other, or to have a p-scale radius. So I will use pop grains for that, which simulates those particles like they are pieces of sand. But the pop grains requires p-scale, so I'll do another pop VOP, call it p-scale, and I will create here an attribute called p-scale, which is a float as a value of 0, and I will assign a value to it from a constant of 0.1 for beginning. Okay, now let's see the movement. Now the particles are not crossing each other anymore, not intersecting anymore. They go around each other, and the movement looks more fluid. So I'm happy with what we have. Now let's charge them with values which are positive and negative and feed them into the magnetic field. But before doing that, let's make a change. Actually, if you follow my tutorial for now, step by step, you should make the change, because I made it in a break. And that change is to go at curl noise and increase the frequency from 1 to 3 all over, to make it more curly, let's say. Okay, so let's bring those points into our magnetic field system. Let's make an out, call a null, actually, a null called magnetic points. Let's make it black. Let's also bring the sphere. And call it sun sphere. Let's see how they look together. Let's give a color to the sun, a color black to occlude the back face particles. We don't have UV, so there is a conflict here, so let's just change the way we visualize it. Okay, so back into the magnetic field system, we should feed here our newly created particles. Okay, so I need half of those points to be charged positively and half of it to be negative, to have an equal number of positive poles and an equal number of negative poles. So to do that, I will use also wrangle mode. It's faster, and we will say here like that: let's create a float called sunspots. And give it a random value from etinum, from each number of each point, and multiply this with a feed. Now let's do a condition. If if our sunspots are bigger than 0.5, then make them positive pole. And this time we'll give to our charges a smaller value than 1, because they are very close to each other and they will repel too much otherwise. And else is pole negative. Okay, so now let's cross our fingers and see what's going on. First, the bound covers our sphere correctly. These offsets. Let's calculate the volume angle. Let's make this red, like all other wrangles. And now, let's see. Wow, it's working. Let's make the value a little bit more visible. Let's increase the number of points in the scatter to, let's say, 4,000 to see more. I can get even more than that, 5,000. Sorry. And this is our magnetic field. And if we animate this, it will take a while. So I'll make a play blast and come back soon after. So I did a short preview of my magnetic field, and I can say that I'm quite happy with what I got. I have small fields, big fields, closed ones, open ones. And the nicest thing about this setup is that you can play with it by yourself and adjust it to your own preferences. You can modify the speed of the particles that run over the surface of the sun. You can modify their number, maybe once more. You can modify the intensity of the plus and minus poles. You can even duplicate the system and make a special system only for big explosions and a denser, faster one for the small ones. So we have now a system that works and that will be the driving force behind our particles. Now we got to build a particle system that will be influenced by this vector field. But before that, I want to show you my modification that I did in the system. Not so many. First, I bring the sun body to visualize it together with a magnetic field. At the bound, I changed the bound from box. I used to have a box bound, and I changed it from box to sphere. And I increased the lower padding and the upper padding to 3. I decreased the number of the particles from the scatter point to have a faster preview. And that's about it for a moment. And see you with the next part of our tutorial, which will be building the real explosions.